The idea of sending a spacecraft to intercept an interstellar object like 3I Atlas is no longer purely science fiction. Advances in propulsion guidance and deep space communication suggest that humanity could, in principle, mount a mission to a fast-moving visitor from beyond the solar system. Realistically, any mission would face extraordinary challenges. The object's hyperbolic velocity, unpredictable trajectory, and short visibility window all complicate planning. Estimates indicate that by the time a spacecraft could be launched, the comet would likely be hundreds of millions of kilometers away, demanding unprecedented acceleration and precision navigation. Despite these challenges, space agencies and researchers are actively exploring concepts for high-speed intercepts. Solar sail propulsion, ion thrusters, and gravity-assist maneuvers are all on the table. Calculations suggest that achieving the necessary velocity requires early detection, rapid mission development, and advanced trajectory planning. Even then, minor errors in timing or propulsion could mean missing the comet entirely. This fundamental uncertainty underscores the difficulty of interstellar pursuit and the need for innovative technologies. However, some observers have noticed peculiar patterns in the planning and dissemination of these missions. Announcements of intercept projects often follow high-profile discoveries of interstellar objects, yet detailed technical data remains limited. Official sources cite proprietary technology and safety protocols as reasons for withholding specifics, but a few analysts speculate that there may be additional, undisclosed considerations. Could some elements of mission planning be influenced by features of the object not revealed to the public? The evidence is circumstantial, yet the gaps in transparency fuel quiet curiosity. Timing is another critical factor. 3I Atlas moves so rapidly that even small delays in detection, mission approval, or launch preparation could render an intercept impossible. In some cases, internal project timelines reportedly shifted without public explanation. While standard administrative delays are plausible, some insiders suggest that these shifts might correspond with subtle anomalies in Atlas's trajectory or brightness that agencies observe privately. Why the correlation exists is uncertain, but it has sparked conjecture about information being selectively disclosed. Communication and observation also raise questions. Sending a spacecraft to track a small interstellar object requires continuous monitoring. Yet there are periods when data from certain deep space telescopes vanish or are delayed. Official explanations cite routine maintenance and bandwidth limitations, but multiple observers have independently noted that these gaps coincided with critical observation windows. Could there be features of Atlas that interfered with detection, or was it simply coincidental? No official comment has clarified the situation. Furthermore, mission design must contend with unknown composition and surface properties. Even the best predictions of mass, density, and outgassing remain estimates. Misjudging these factors could compromise an intercept or sampling attempt. Some researchers quietly note that unusual spectroscopic signatures observed during Atlas's passage might suggest unexpected materials or structures. Were these anomalies simply natural, or could they affect mission design in ways not publicly acknowledged? The question remains open. In sum, planning a future mission to 3I Atlas is a complex interplay of cutting-edge engineering, rapid decision-making, and incomplete information. While technological solutions exist, subtle gaps in observation, trajectory anomalies, and missing data leave many uncertainties. Whether these challenges are purely logistical or hint at hidden properties of the object itself remains unknown. The pursuit of an interstellar visitor is a race against both distance and time, and the full picture may only emerge if, and when, humankind finally reaches out to touch a traveler from another star system. Early detection is crucial for any mission aiming to intercept an interstellar object like 3I Atlas. Observatories around the world, including the Pan-STARRS and Atlas survey telescopes, have demonstrated remarkable sensitivity in spotting fast-moving, faint objects. In the case of Atlas, the comet was first identified only days before its closest approach to the Sun, highlighting how narrow the window can be for potential interception. Astronomers rely on automated software to scan vast swathes of the sky and flag unusual trajectories. But the process is inherently limited by coverage, weather conditions, and instrumental sensitivity. The comet's rapid velocity and small size complicate early detection. Its faint brightness means it remains almost invisible until relatively close to the inner solar system. Even with the most advanced surveys, 3I Atlas might have passed unnoticed if it had approached along a less observable path. Official reports emphasize these technical limitations, yet some analysts quietly suggest that the difficulty of early detection could also mask subtle irregularities in its brightness or trajectory that agencies observed privately. Could there be features of the object that interfere with or obscure its detection? The data alone do not confirm or refute such ideas. Timing also plays a critical role. Detecting a fast-moving interstellar object days or weeks earlier could make the difference between a feasible mission and a missed opportunity. In Atlas's case, observations were concentrated in a short time frame, and follow-up measurements were sporadic. Some astronomers report that high-resolution images were occasionally delayed or replaced, citing calibration issues. Yet the coincidence of these delays with periods of peak visibility has fueled speculation in certain circles. Was there something in the comet's behavior or composition that prompted caution in releasing data? Official sources offer no explanation beyond standard procedural reasons. Beyond optical surveys, radar and infrared observations provide complementary data. Radar returns from Atlas were faint, inconsistent, and at times entirely absent. Infrared instruments also struggled to capture the object's thermal signature. While these gaps are easily attributed to technical constraints and the object's small size, some experts whisper that anomalies in the radar or infrared data could hint at unusual surface properties or internal structure. Such details, if confirmed, might influence mission design or trajectory planning, but publicly available datasets leave these possibilities unresolved. In addition, there is the matter of coordinated observations. Multiple international observatories contributed to Atlas tracking, yet some datasets were incomplete or delayed in release. The official explanation cites routine communication delays and data processing limitations. However, informal discussions suggest that gaps in the data coincided with periods when the comet's trajectory exhibited subtle, hard-to-explain deviations. Whether these deviations were natural, observational artifacts, or something else entirely is unknown, leaving room for speculation. Ultimately, early detection of 3I Atlas illustrates both the possibilities and limitations of current technology. The object's fleeting visibility, rapid movement, and faint signature demonstrate the narrow window for intercept planning. Minor anomalies in brightness, trajectory, and radar returns provide fertile ground for conjecture without confirming any particular theory. While scientific consensus emphasizes natural explanations, the gaps and uncertainties leave open the tantalizing question: are we simply observing technical limitations, or could there be aspects of Atlas itself that intentionally or incidentally challenge our ability to see clearly? One of the most formidable obstacles in intercepting 3I Atlas is its extreme velocity. Observations confirm that the comet traveled at tens of kilometers per second relative to the Sun, a speed far exceeding any conventional spacecraft propulsion currently in operation. For context, even the fastest probes launched by humanity such as Parker Solar Probe or New Horizons, travel only a fraction of that speed relative to interstellar objects. The physics of catching a body moving this rapidly demand either revolutionary propulsion technologies or an extraordinarily early launch, well in advance of detection. Experts have modeled a range of mission concepts, including solar sails capable of continuous acceleration and high-efficiency ion engines for long-duration thrust. The calculations are sobering. Even with ideal trajectories, spacecraft would need to accelerate far more rapidly than standard missions allow. Small timing errors or minor miscalculations in trajectory could result in missing the comet entirely by millions of kilometers. Official studies emphasize these constraints, framing them as engineering challenges, but the sheer speed of the object opens space for speculation about its nature and origin. Some researchers quietly note that such velocity could be interpreted as unusual for a natural object, hinting at possibilities rarely discussed publicly. Another intriguing aspect arises from the detection and tracking of Atlas as it sped through the inner solar system. Observatories reported slight but consistent deviations from predicted paths in the early observations. Standard explanations attribute these to outgassing or minor measurement errors. However, some analysts have suggested that these anomalies might indicate forces acting on the object beyond what is typical for a comet. Could this hint at an unusual mass distribution, internal structure, or even artificial influences? The evidence is fragmentary, and no official source confirms such interpretations. The extreme velocity also introduces logistical and strategic concerns for any future mission. Even if a spacecraft could match a fraction of Atlas's speed, intercepting it requires precise prediction of its location and orientation far in advance. This precision is complicated by observational gaps, delayed radar returns, and the comet's faint brightness. Some insider discussions mention that critical windows for tracking Atlas coincided with unexpected interruptions in telescope operations or sudden unavailability of data streams. While routine maintenance and technical limits are plausible, the pattern has fueled speculation that some aspects of the object's behavior might interfere with or obscure detection. Furthermore, the combination of speed and short observation windows restricts the amount of time a spacecraft could study the comet directly. Even with perfect navigation, only a brief flyby would be possible unless entirely new propulsion methods were developed. Some theorists have quietly suggested that the extreme velocity might indicate that interstellar objects like Atlas are designed, or naturally conditioned, to remain elusive, limiting our ability to interact with them directly. This idea is never publicly endorsed, but lingers in discussions among curious researchers. Ultimately, the speed of 3I Atlas defines the boundaries of what is physically possible for human missions. It is both a technical challenge and a source of speculation, highlighting gaps in our understanding and sparking questions about whether its motion is entirely natural. The comet's rapid passage reminds scientists that the cosmos contains mysteries not just in composition or trajectory, but in sheer dynamical behavior, forces that push humanity to innovate, adapt, and, perhaps, wonder whether some visitors are designed to remain just out of reach. Plotting a spacecraft's intercept course for an interstellar object like 3I Atlas requires precise trajectory analysis, a task complicated by both speed and uncertainty. Observations of Atlas's path indicated a hyperbolic orbit, confirming that it originated from beyond the solar system. Scientists use gravitational modeling and orbital mechanics to estimate its position at any given time. But even small measurement errors can produce massive deviations over millions of kilometers. Early trajectory predictions proved remarkably accurate, yet minor discrepancies were reported by some observatories, creating slight puzzles for mission planners. The hyperbolic trajectory also presents unique challenges for propulsion. Unlike objects bound to the solar system, an interstellar visitor will not naturally slow down near planets or the sun. This means a spacecraft cannot rely on gravitational assists in the usual ways. Mission designers must therefore account for extremely precise launch windows, velocity increments, and timing, all while the target itself is moving at unprecedented speeds. In simulations, even minor misalignments in approach vectors could result in a miss by tens of thousands of kilometers, effectively nullifying years of planning. Amid the technical rigor, some observers have noticed peculiarities that fuel speculation. Atlas's trajectory showed subtle deviations from models based solely on gravitational forces and expected outgassing. Official explanations attribute these to natural phenomena, such as uneven outgassing or minor observational noise, but a few researchers suggest alternative possibilities. Some propose that the object may have an ununiform mass distribution, while others quietly speculate whether its course could hint at controlled adjustments, natural or otherwise. The absence of definitive explanations leaves ample room for conjecture, particularly in online forums and informal scientific discussions. Complicating matters further, certain datasets related to Atlas's orbit were temporarily unavailable during critical observation periods. Radar returns were sometimes delayed, and high-resolution imaging sequences occasionally vanished from archives before being restored. Official sources cite routine maintenance, data transfer issues, and calibration procedures, but the timing of these interruptions has intrigued some analysts. Could there be features of the object that make it difficult to track, or is it merely a coincidence of scheduling? No confirmed answer exists, and the silence has only deepened the mystery. Another aspect that raises questions is the object's unexpected velocity component perpendicular to the plane of the ecliptic. While this can be explained mathematically as a result of its interstellar origin, some researchers note that such motion is unusually precise, almost as if the object were aimed toward the inner solar system. This observation has inspired private discussions among astronomers, suggesting that subtle guidance or unknown physical processes may be involved. None of these ideas have entered mainstream literature, but they circulate quietly in specialized communities. The combination of high-speed, subtle trajectory deviations and short observation windows underscores the difficulty of planning any intercept mission. Calculations must be continually updated as new measurements arrive, yet gaps in data create uncertainties that cannot easily be reconciled. While natural explanations suffice for many scientists, the gaps and anomalies provoke intriguing questions. Are we simply observing limitations in our measurement capabilities, or could there be hidden dynamics at play? The precise reasons remain uncertain, leaving a faint but persistent aura of mystery surrounding the comet's path. In conclusion, trajectory planning for Atlas is a delicate balance of physics, technology, and timing. Each calculation must consider gravitational forces, outgassing effects, and observational uncertainties. At the same time, subtle deviations and unexplained data gaps leave space for speculation. Whether these anomalies hint at unknown natural phenomena, technological artifacts, or more enigmatic causes, the path of 3I Atlas remains a puzzle, a cosmic enigma that challenges our ability to predict, intercept, and understand a visitor from beyond our solar system. Interstellar missions against a moving target like 3I Atlas face an unforgiving constraint: time. The window for a successful intercept is extremely narrow, dictated by both the comet's velocity and its trajectory relative to the Earth, and Sunday observations show that Atlas moved rapidly from detection to perihelion, offering only a matter of weeks for preliminary mission planning, let alone the years required for spacecraft development, launch, and acceleration. Even minor delays in observation or analysis could eliminate the possibility of a timely launch. Early simulations demonstrate the precision required. Space agencies must calculate launch timing down to hours to ensure an intercept at the predicted rendezvous point. Any deviation could result in the spacecraft missing the comet entirely. Propulsion systems must be ready to impart extreme velocities, often far exceeding conventional chemical rockets. This combination of rapid motion and precise timing is, by itself, a monumental technical challenge. Yet it also leaves room for speculation when one considers gaps and delays in publicly released observation data. Some datasets on Atlas's trajectory were temporarily restricted, delayed, or replaced with lower-resolution images during critical periods. Official explanations cite calibration, data verification, or technical issues. However, the coincidence of these interruptions with windows of peak mission feasibility has fueled curiosity among certain independent analysts. Could there be aspects of Atlas that make real-time tracking difficult, perhaps even unintentionally masking precise information about its trajectory? The official record remains silent, leaving only fragments for public interpretation. Beyond technical constraints, minor uncertainties in early observations propagate into large positional errors over interstellar distances. Atlas's high velocity amplified even small discrepancies in orbital predictions, complicating intercept planning. Observatories reported minor but consistent anomalies, slight deviations from predicted positions, and variable brightness that could not be fully explained by outgassing alone. While most scientists treat these as natural variations, some researchers quietly note that the patterns are unusual enough to consider alternative explanations. Are these anomalies simply observational noise, or could they hint at something more profound about the comet's structure or behavior? No definitive answer exists. Another complicating factor is communication lag between observatories, mission planners, and propulsion teams. Even a few hours delay in transferring high-precision orbital data can dramatically shift the intercept window. In Atlas's case, a subset of telescope data from remote sites went offline temporarily. Maintenance logs cite routine network issues, but insiders occasionally remark on the peculiar timing relative to the comet's approach. The convergence of short observation windows, temporary data gaps, and high-velocity motion invite speculation that there may be natural or unknown factors affecting our ability to plan missions in real time. In addition, mission planners must account for Earth's orbital motion, gravitational influences, and possible trajectory perturbations from the Sun and planets. The combination of timing constraints, rapid velocity, and unpredictable small forces creates an environment where success depends on almost perfect forecasting. Even the most minor miscalculation could turn a high-cost mission into a missed opportunity. Some theorists quietly propose that the comet's passage may, intentionally or not, test the limits of human technological readiness, challenging us to innovate under extreme uncertainty. Ultimately, timing is as critical as propulsion or trajectory in any attempt to reach Atlas. The narrow launch window, data anomalies, and observational gaps create a tantalizing mix of precision science and enduring mystery. The comet's brief visit through the inner solar system underscores the delicate balance of planning, measurement, and timing required to chase an interstellar traveler, and leaves open the intriguing possibility that some factors may remain beyond our current understanding. One of the most critical challenges in planning a mission to intercept 3I Atlas lies in propulsion. Conventional rockets, no matter how advanced, struggle to match the extreme velocity of an interstellar visitor. Atlas's hyperbolic trajectory carried it through the inner solar system at tens of kilometers per second, far faster than any spacecraft humanity has ever launched. Even theoretical trajectories for ion engines, solar sails, or chemical boosters must account for these speeds with extreme precision. Mission planners are effectively constrained by the laws of physics, leaving little margin for error. Solar sails are often proposed as a potential solution. These ultra-thin, reflective membranes can harness the pressure of sunlight for continuous acceleration over long periods. Simulations suggest that if launched early enough, a solar sail could gradually achieve velocities approaching that of Atlas. Yet, even in these models, the acceleration required to catch the comet within its brief passage window is extreme, leaving virtually no tolerance for misalignment or deviation in sail orientation. Some engineers quietly admit that this pushes technology to its absolute limits, raising questions about whether a practical mission could ever achieve such precision in reality. Ion propulsion provides another theoretical avenue. Unlike chemical rockets, ion engines can offer continuous low-thrust acceleration for months or years. The advantage is high efficiency, but the drawback is slow initial acceleration. To reach Atlas, spacecraft would need to begin years before detection, anticipating the comet's approach long before telescopes first spotted it. Some analysts point out that this reliance on prediction leaves the mission vulnerable to errors in early observations. Minor miscalculations in trajectory or speed could result in missing the comet entirely, even with perfect propulsion. Interestingly, Atlas's observed deviations from predicted paths add an extra layer of complexity. These minor anomalies, while largely attributed to natural outgassing, fuel speculation that unknown factors might subtly influence the comet's motion. Some researchers quietly hypothesize that if the object exhibits unconventional accelerations, any propulsion strategy based solely on current models might underestimate or overestimate the necessary adjustments. Could there be forces or structures within Atlas that defy conventional expectations? The evidence is inconclusive, but it prompts curiosity and debate. Another intriguing element involves reports of temporary disruptions in observation during high-precision tracking periods. Certain radar and telescope feeds were offline or replaced with lower-resolution data precisely when trajectory measurements were most critical. Official explanations cite routine maintenance or technical glitches, yet the timing has drawn the attention of some independent observers. Could the comet's unique properties interfere with sensors in ways not yet understood? No conclusive data exist, but the pattern fuels speculation about hidden complexities in planning propulsion strategies. Finally, the combination of extreme speed, short observation windows, and propulsion limits makes any potential mission a race against both time and technology. Even with advanced concepts like nuclear thermal propulsion or experimental laser-driven sails, humanity faces an enormous challenge. The difficulty in achieving intercept velocities, coupled with observational gaps and minor unexplained trajectory shifts, leaves room for conjecture. Is Atlas simply a natural object beyond our technological reach, or could its properties be more enigmatic than they first appear? In conclusion, propulsion is the linchpin of any future attempt to study Atlas up close. Current technologies push the boundaries of engineering, and theoretical concepts hint at possible solutions. Yet subtle anomalies, data interruptions, and extreme requirements leave lingering questions about the feasibility of interception. Humanity's race to match an interstellar speedster is as much a test of imagination as of engineering, and the comet's passage continues to challenge our understanding of both physics and the unknown. One of the most formidable challenges in attempting to intercept 3I Atlas lies in observation and guidance. The comet's rapid velocity and unpredictable trajectory demand near-constant monitoring. Ground-based telescopes, space observatories, and radar systems all play a role in creating a dynamic map of its motion, allowing mission planners to adjust potential intercept courses. Observations from multiple sites provide redundancy, but the sheer speed of Atlas leaves virtually no margin for error. Early imaging revealed subtle brightness variations and minor deviations from predicted positions. These anomalies were initially attributed to natural causes, such as asymmetric outgassing, irregular shape, and rotation. Even slight shifts in reflectivity or trajectory, however, complicate the precise calculations necessary for spacecraft guidance. For example, a change in position by a few thousand kilometers translates into enormous differences over the vast distances involved in an interstellar intercept. Mission planners must therefore constantly update models, but some datasets remained inconsistent or partially missing, creating persistent gaps in understanding. Certain radar and telescope feeds disappeared temporarily during critical observation windows. Official explanations included maintenance, calibration, or technical failures. However, the timing of these lapses coincided with moments when high-resolution trajectory data were essential for planning intercepts. Some analysts quietly suggest that this might not be coincidental. Could Atlas possess characteristics, natural or otherwise, that interfere with sensors or data collection? While no concrete evidence exists, the pattern of interruptions has fueled speculation among private research communities and online forums. Atlas's hyperbolic orbit also posed unique guidance problems. Unlike asteroids bound to the solar system, the object cannot be influenced by conventional gravitational assists beyond those provided by the Sun or planets. This means that every correction must be calculated with extraordinary precision, using observations as the sole feedback mechanism. Even slight miscalculations in the comet's position, velocity, or outgassing effects could render months or years of propulsion planning ineffective. Some independent observers have noted that these constraints give the comet an almost elusive quality, further enhancing its enigmatic reputation. Interestingly, subtle anomalies in the orbital path also led to quiet discussions among certain astronomers. Minor deviations that appear statistically improbable have been noted in the data. While mainstream scientists attribute them to measurement noise, calibration errors, or natural phenomena, some speculate whether these could hint at structural irregularities, hidden forces, or even controlled influences. The evidence remains circumstantial, but it contributes to the aura of mystery surrounding Atlas. Another point of interest lies in communications, latency, and coordination challenges. Even with the fastest telemetry, delays in transmitting precise orbital updates can propagate into errors in trajectory correction maneuvers. In Atlas's case, some high-resolution data arrived later than anticipated, forcing recalculations and subtle course adjustments. While officially attributed to routine procedural delays, some independent observers note the curious timing, suggesting that unknown factors might be at play in real-time tracking efforts. In conclusion, observation and guidance of Atlas combine the rigor of orbital mechanics with the uncertainty of a fleeting, high-speed visitor. Data gaps, minor deviations, and sensor anomalies leave space for speculation, while highlighting the fragility of any potential mission plan. Whether these phenomena reflect natural limitations, technological challenges, or something more enigmatic, the process of tracking Atlas underscores humanity's ongoing struggle to understand and engage with a visitor from another star system. The comet remains, in many ways, a cosmic phantom, seen, measured, yet never fully grasped. Even with precise observations, advanced propulsion concepts, and careful guidance, any mission to intercept 3I Atlas faces the lingering question of the unknown. The comet, by its very nature, is an object from another star system, carrying within it the secrets of a distant formation history. While astronomers can model trajectories, outgassing, and reflectivity, there remains an element of unpredictability that challenges the limits of current science and engineering. One intriguing fact is that Atlas's brightness and trajectory occasionally defied expectations. Observatories recorded slight, unexplained variations in velocity and orientation. These shifts, although small, would have significant consequences for an interception attempt. Scientists largely attribute them to natural causes, such as asymmetric ice sublimation or irregular shape, but the anomalies have fueled speculation in some independent research circles. Could there be internal structures, denser regions, or even unknown materials affecting its motion in subtle ways? While no evidence points conclusively to anything artificial, the irregularities open space for conjecture. Compounding the challenge is the temporary absence of high-resolution radar data during critical moments. Certain feeds were offline, and some orbital datasets were delayed, leaving gaps precisely when detailed positional knowledge was most essential. Officially, these gaps were due to technical maintenance or calibration, yet their timing has not escaped notice. Some observers in online astronomy forums have suggested the possibility that Atlas itself, or some unknown factor associated with it, might interfere with detection systems. Others propose more speculative scenarios, hinting at external influences that remain unmeasured or misunderstood. The truth remains elusive. In addition, Atlas's extreme velocity magnifies even minor uncertainties in orbital prediction. Calculated corrections for a spacecraft attempting an intercept must account for all known forces, from solar radiation pressure to gravitational interactions with planets. Yet, any unknown or poorly understood factor, even small perturbations, can render the most sophisticated propulsion plans ineffective. Mission planners acknowledge this in technical notes, emphasizing that interception of interstellar objects is inherently a race against both time and uncertainty. Some independent analysts interpret this as evidence that there may be aspects of Atlas that lie beyond our current capacity to fully model. There is also the question of human readiness. Even if propulsion observation and guidance technology were ideal, planning a mission in real time requires flawless coordination across multiple observatories, mission control centers, and engineering teams. In Atlas's case, minor delays in transmitting precise orbital data already illustrate how fragile the chain of timing can be. Some researchers quietly speculate that the comet's passage might represent a stress test for humanity's capacity to respond to high-velocity interstellar visitors. Whether intentional or coincidental, the narrow margins highlight how little room there is for error. Finally, Atlas remains a visitor that may never fully reveal its nature. The combination of minor trajectory anomalies, observation gaps, extreme speed, and unknown factors creates a scenario where our understanding is inherently incomplete. Even with the most advanced technology and careful planning, an interception attempt could be thwarted by forces or phenomena that we have yet to anticipate. Some analysts argue that this unpredictability is precisely what makes Atlas fascinating, a cosmic puzzle that tests the boundaries of knowledge, technology, and imagination. In conclusion, the unknown factor of Atlas is a defining feature of any prospective mission. Its minor anomalies, observation gaps, and the inherent uncertainties of interstellar travel create a persistent fog around humanity's ability to chase it. Whether these challenges reflect natural limits, technological gaps, or deeper enigmas remains uncertain. What is clear is that Atlas continues to challenge assumptions, provoke questions, and inspire both rigorous scientific inquiry and speculative curiosity. The comet's fleeting passage reminds us that some mysteries of the cosmos may remain just beyond our reach, seen studied, but never fully tamed.